Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical. And in this particular topic, we will be talking about the different types of the metals, their mechanical properties and the related metallurgy, and how these the metallurgical aspects affect the metal forming process. So, ease of the metal forming is primarily governed by the yield strength and the ductility, apart from the work hardening tendency, because most of the sheet metal forming thing is done under the room temperature condition by cold forming. Okay. So, if the material is showing the low work hardening tendency, then our ease of the metal forming will be better. If the metal is of the high ductility, our ease of the metal forming will be high because of the limited or low cracking or fracture tendency. And similarly, if the yield strength of the metal is low, then also it will be leading to the reduced the forces and energy required for the metal forming. So, we have to see that how the metallurgical aspects affecting the work hardening tendency, yield strength and the ductility, which in turn will be affecting the metal ease of the metal forming. Okay. So, initially we will be starting this presentation with the factors that are governing or controlling the ease of metal forming, like yield strength, ductility and work hardening. Okay. And thereafter we will see that how the structural aspects associated with the different the common metals which are used in metal forming affects the mechanical properties like yield strength and ductility and work hardening tendency. Okay. So, in the metallurgical aspects, what we are interested basically is that the how the microstructural features, okay, like the size of grains and the phases which are present. So, these are the two important aspects, the size of the grains and the phases which are present, how these two will be affecting the percentage elongation, okay, and the yield strength and the work hardening tendency. So, we will try to look into these aspects related with the metallurgy and the metal forming. So, starting with the first one, when the sheet metal is subjected to the plastic deformation, we can find that there is a surface which is rough and with the various kind of the features which may spoil or degrade the aesthetics of the components which has been produced by the metal forming or sheet metal forming approach. So, one is the like orange peel. Orange peel is about the surface roughening at the grain size level, which means the surfaces may look like little rough at the grain size level. Okay. So, this roughness is of like say 5 micrometer, 10 micrometer as per the grain size, which will be visible also. So, roughening at the grain size level, and this primarily occurs due to the different orientation of the neighboring grains. So, say there is one grain, another grain, third grain, fourth grain, all these grains have the atomic arrangement in the different ways, which we say as orientation of the atom in each grain is different. So, that will be leading to the different kind of the appearance when the metal is subjected to the plastic deformation and when these the grains are revealed. Okay. So, the orange peel is one which is indicating the surface roughness at the grain size level, primarily due to the different orientation of the neighboring grains. Okay. Few grains may deform differently from other grains in the lateral direction, and that is what results in this kind of the roughening. Okay. So, if we go with the refinement of the grains as compared to the coarse grains, if we have fine grains, then the peel orange tendency is minimized. Okay. Ridging is observed is like this, where the certain the deformation in certain directions is visible at the surface. So, the ridging in ferritic stainless steel or in aluminum alloys, this is particularly observed when a cluster of grains having the different orientation. So, this is one cluster having the different grains, and in this cluster grains are having a particular orientation. Then there is another cluster of the grains in which the grains are oriented in the different direction. Okay. So, when the cluster of the grains have the different orientations, then obviously these clusters will be deforming differently in the lateral direction. So, these clusters elongate selectively or differently in the different directions, and that is what causes the ridging. Okay. So as far as the difference is concerned, peel orange and the ridging is here, this is about the surface roughening at the grain size level due to the different orientations of the neighboring grains. Okay. But here what we talk about, cluster of the grains having the different orientations. So, where few clusters elongate or deform selectively in certain directions, leading to the ridges. Okay. Then the stretcher strains, these are the features indicating the stretcher strains, and this occurs primarily due to the incomplete leader band formation, especially in the low carbon steels showing the yield point, or the steels showing the upper yield point and the lower yield point, like this, say upper yield point and the lower yield point. So, this kind of the metals which show yield point, they and experiencing the incomplete leader bends, they show the stretcher strains. Okay. So, here as far as the ease of the metal forming is concerned, as I have said, that if the material is ductile, whether it is 10% or 50% ductility, in case of the 50% ductility, metal can be stretched to the greater extent without tendency of the crack initiation and the fracture. But if the metal is having limited ductility, in that case metal will show the cracking tendency, its formability will be limited. So, it is very important that material is ductile, which we measure in terms of the percentage elongation or percentage reduction in area, that is done through the tensile test or the bend test. So, for example, here this one schematic diagram, say for one metal, if we say metal is subjected to the tensile loading, then the variation in engineering stress and strain A to B shows the elastic section where there is a direct linear relationship. Then we have the upper yield point, then the lower yield point at C, and this is the leader bend section, and then thereafter at the end of the leader bend section we find the work hardening. This is the plastic deformation zone. Plastic deformation starts very much here, but here this is where the work hardening will be happening, and at E the necking will start. Okay, and the fracture will be taking at the F. So, whatever is the strain occurring in the metal at the fracture stage, that will be indicating the percentage elongation. Okay. So, that will be indicating the ductility in terms of the percentage elongation. Greater is the engineering strain, greater will be the ductility of the material. Okay. So, this is one way. It is possible, like one metal shows the one curve of this kind, another shows like this kind. So, in this case the ductility of the metal is much higher than the another material. So, the metal A and metal B. So, metal B will be showing the greater ductility, more easier metal forming tendency as compared to the metal A, because not just the ductility, but it will also be deforming plastically at the lower level of stress as compared to the metal A. Okay. So, the yield strength and the percentage elongation, these are the two very important aspects as far as the ease of the metal forming is concerned. Okay. So, metals, like as I have said, the upper and lower yield point, this kind of the behavior is shown by most of the carbon steels. Okay, where upper yield point and the lower yield point, and at the lower yield point stress level the material deforms plastically without need of much higher level of stress. So, this strain is about like 1 to 3%. Okay. So, the leader band strain is about 1 to 3%. This typical behavior is observed in case of the carbon steels, but like stainless steels and aluminum alloys, they do not show any particular yield point, and in that case what we do, we try to use the 2% of the engineering strain or 3% of the engineering strain, 5%. So, 2 to 5% of the offset, at 2 to 5% of the offset, one line is drawn parallel to the straight line section, and wherever it cuts, that indicates the yield point corresponding to either 2% or 5% of the offset. yield strength. So, accordingly 2% offset stress indicating the yield strength of the material for such kind of the metals which do not show the typical yield point, okay, like carbon steels. Okay. Apart from this, the ductility and yield strength, we have to deal with the work hardening tendency, because when our sheet metal is deformed, material tends to get hardened, and that makes the further deformation difficult because it requires higher force and higher energy. Okay. So, the section where the metal is the plastic deformation and shows that it requires higher and higher level of stresses to cause further deformation, that will be the work hardening or the plastic strain hardening zone. Okay. Different metals show the different strain hardening tendency, like one metal shows like this and another metal shows for same. It is possible like for same strain value, the two are getting work hardened differently, and this is particularly attributed to the stacking fault energy associated with those metals. If the metal is having low stacking fault energy, then it shows the higher work hardening tendency, and the metals with the higher stacking fault energy, they will be showing the lower or lesser work hardening tendency. If the metal is showing lesser work hardening tendency, for the same strain, one will get hardened to the greater extent, while another one will get hardened to the lesser extent. So, this is with the low work hardening tendency, and this is with the high work hardening tendency. Say this is the level where from say plastic deformation starts. So, higher work hardening tendency means it will require greater and greater stresses with the increasing the plastic strain value, and that will make the metal sheet forming job little difficult. So, that is why the strain hardening is important parameter as far as the sheet ease of the sheet metal forming is concerned. Now, we will try to see the another aspect, that is about the strain aging. Okay. In strain aging, what happens, like say the metal is subjected to the plastic deformation, say metal is subject to the loading, and then after loading, if it is unloaded and then again it is loaded, then there will not be any change in the yield point. But if the metal is subject to the plastic deformation and then loaded and then again reloaded after some time, then we will find the another the yield point level. Okay. Initially the yield point level may be here, but if the reloading is done after some gap, then we will find the change in the yield point, that will be higher. So, this higher yield point is attributed to the aging or aging after the plastic deformation. That is why it is known as strain aging. Okay. So, the strain aging, so what happens when the load is applied and load, say you have applied load like this is one case. So, load is applied subject to little plastic deformation and immediately we apply another load. So, there will not be any change, it will start showing the work hardening like this. Okay. But if we deform the material and leave it for some time, and then again if it is subjected to the external loading, then it will show new yield point. Okay. That will be further higher level. So, this change in the strain value, say this is the kind of curve which is obtained immediately after the loading, and when it is done say after some time, then time lapsed loading, then we will find the new yield point. So, the difference can be observed by loading and unloading, whether the metal is experiencing any kind of the change in yield point due to the plastic deformation, due to the strain aging effect, that can simply be checked by loading and unloading after the plastic deformation. So, if we do after unloading, if we do reloading immediately, then there will not be any difference in the yield point. Okay. But if after a gap, if the loading is done, then we will find the new yield point which is higher. Okay. So, this higher level of the yield point will be considered as undesirable aspect from the metal forming is concerned, as far as the metal forming is concerned. Okay. So, strain aging happens, why there is another new yield point after some gap we find, say metal is deformed plastically to some extent, then it is unloaded and kept under room temperature conditions for some time. Okay. And then when it is subject to the reloading, we will find the new yield point which is higher. So, this higher yield point is attributed to the strain aging, and why, what is the reason behind that? The strain aging happens due to the locking of dislocations by interstitial carbon and nitrogen. So, when metal is subjected to the plastic deformation, we will see lot of dislocations will be created, okay, like this. So, and these dislocations are locked in by the diffusion of interstitial atoms like carbon and nitrogen. Okay. So, these carbon and nitrogen get segregated at these dislocations. Once these get segregated, they will be locking the dislocations, means they will be making the dislocation movements difficult, or indirectly they will require higher level of stress to cause the movement of dislocations to facilitate the plastic deformation. And therefore, the locking of dislocations by this carbon and nitrogen makes the dislocation movements difficult, and thereby it increases the yield strength. Okay. So, if we do immediately, then there will not be any diffusion, there will not be any locking of the dislocations by the interstitial atoms like carbon and nitrogen. So, there will not be any change in the yield point. Okay. Since the strain aging is based on the locking of dislocations by these interstitial atoms, which is based on this locking is based on the diffusion of atoms towards the dislocations, and it is based on the distance, it is based on the diffusion. So, it needs some time and temperature. So, if after deformation of the metal, if it is kept for very short time, then the absence of the diffusion or very limited diffusion may not be leading to the any change in the strain plastic, sorry, may not be leading to the any change in the yield strength. But if after plastic deformation, if the component is kept aside for some time, permitting the movement of carbon and nitrogen to lock in the dislocations, then it will be leading to the strain aging and increase in yield strength. If the after plastic deformation at little higher temperature, if component is kept at a higher temperature for some time, then strain aging will be happening very quickly. It will not take long time, and that is why what we may find at little higher temperature, like it may happen like this. So, here what it shows, this kind of the variation in engineering stress and strain, what it shows that the strain aging at a higher temperature is happening quickly. When the deformation is happening, aging is also happening at the same time. So, at room temperature, strain aging may take little longer, but at a high temperature it may be quick. Okay. So, this time lapsed loading causes the increase in the yield strength, and of course, the reduction in ductility. And so, this is basically the hardening and the little embrittlement. And if the loading is done immediately after the unloading, then there will not be any change in the yield strength. Okay. So, the deformation of the metal, once the same metal is subjected to the stress level up to the upper yield point, then the further deformation will be happening at a much lower level of stress, and the deformation will continue to happen without any further increase in the stress being applied. So, this deformation which is happening without any increase in the stress being applied is called the Luder strain. Okay. And this will be producing the Luder band. Luder bands form due to the extension at the lower stress yield point. Luder strain or the yield point elongation is typically 1 to 3%. So, this belongs to 1 to 3% of the strain. Only after the Luder band formation, that is this, at the end of the Luder band formation, metal is subjected to the strain hardening. So, this strain hardening zone will be reflecting only at the end of the Luder band formation zone. And once this section of the work hardening, this section continues, and as soon as it reaches to the ultimate point at E, then the necking will start. So, up to the, like say, in the D to E zone, the elongation is uniform or the plastic deformation is uniform, but as soon as it reaches to the E, necking at the somewhere in the middle, means localized reduction in cross section in the middle will start, and that is termed as the necking. So, necking will be happening like this somewhere, okay, like this. So, this is the localized reduction, and then eventually fracture at the wherever the necking has happened. So, necking basically starts with the nucleation of voids, then the growth of voids, then their coalescence eventually will be leading to the fracture. Strain aging in steels like say low carbon steels, this is observed in low carbon steels like say 0.06% carbon, mostly observed in the rimmed steels, means in these carb oxygen and nitrogen is present, and this is this typical rimmed steel is marketed in cold and cold rolled or in annealed condition. So, basically the rimmed steels having the impurities like oxygen, nitrogen, but certainly the low carbon. So, this shows so this kind of the steels are found more sensitive for the strain aging. Okay. Strain aging will be happening in the killed steel also, but the impurities are more in case of the rimmed steels. However, moreover, the rimmed steels also show greater heterogeneity, like say this is the section. So, at the center carbon percentage is more as compared to that at the surface. So, here the low carbon and here at the center high carbon. So, this is particularly attributed to the oxygen and the air bubble formation at the surface, killing the carbon and reducing the carbon content near the surface layers and resulting in the higher carbon at the center and less at the surface. So, the rimmed steel show chemical heterogeneity due to the oxygen and air bubbles. So, when the impurities are removed by the addition of the impurities like oxygen and nitrogen are removed by adding the elements like manganese, aluminium and silicon. These help in these have very good affinity with the oxygen. So, what happens, oxygen reacts with these elements to get removed. So, killing of the oxygen is basically done with the help of this aluminium, manganese and silicon. So, killed aluminium, silicon or manganese killed steels are more, they show more homogeneity in terms of the chemical, in terms of the chemistry of the steel produced, and these are mostly produced by the continuous casting to minimize the rolling. You see, steel we may produce in form of the ingots or big billets which need to be rolled down. Through number of passes it will be rolled down by gradually reducing the thickness. Okay. So, this requires lot of efforts and energy and resources. So, what is happening nowadays, most of the killed steel is produced through the continuous casting in form of so that in form of thin plates and relatively thinner plates and the sheets. So, that in turn will be helping to minimize the rolling. So, continuous casting is more preferred for avoiding the excessive rolling to bring down the thickness of the components. Okay, forming and mechanical properties, as I have said earlier, the yield strength and ductility, percentage elongation and the work hardening, these are the most important parameters, but there is a combination of the things also. Like if the metal is having low strength, then ductility is high. Okay. If our strength is increasing, the ductility is coming down. Reducing ductility will be showing the increased fracture or cracking tendency. This is one. Similarly, the work hardening tendency is also affected by the metal's yield strength. So, there is a direct relationship which has been identified, like work hardening exponent and has been found to be related like 70 divided by the yield strength of the metal. Okay. So, from the forming point of view, the yield point effect and strain aging effects are undesirable, because if the yield point is high, then it will require greater force and the power for metal forming. If the metal is strain aging, the similar effect will be produced, because reduction of the N and the surface appearance at the surface, it produces the stretch or strain. So, not just the energy requirement is enhanced, but also the surface appearance is also is spoiled. So, in general, strain hardening exponent and the tensile elongation decrease with the increase of the yield strength. That is what I have just said. So, strain aging is predominant in case of the rimmed steel, where there are a lot of impurities, but say if it is say killed steel, where either manganese or silicon or aluminum has been used to take care of the impurities, then we will see that there will be the lot of variation in the work hardening tendency and the properties of the steels. So, properties of the steels vary, or it ranges from like say interstitial free steels with the very low yield strength of 150 with a tensile elongation of the 50%, to the martensitic steel with the strength of 1400 MPa and tensile elongation is 5%. So, there is a complete contrast. Interstitial flea steels offer very low yield strength and very high elongation. These are very good for the metal forming point of view. Okay, metal forming point of view. But on the other hand, if the martensitic steel, if we consider, then the yield strength is very high and ductility is very limited. So, these will be showing very limited formability, and ease of the forming will be very limited. Okay, in case of the, so sigma y and percentage elongation, that is why these are the very key parameters in terms of the, if you want to judge the ease of the metal forming. So, the cold rolled low carbon steels are almost always sold in the annealed and the temper rolled conditions, and they contain these cold rolled low carbon steels, they contain low carbon like 0.06% carbon and the manganese 0.3 to 0.5%. Aluminum kiln steels show the strain aging at the temperature at the baking the paint, like say the components, a lot of components is manufactured using the sheet metal forming processes, which are subjected to the painting just to give the better appearance and protect it from the corrosion. And then so these painted things are subjected to the baking. During the baking, the metal gains the strength due to the strain aging. Okay, so aluminum kiln steels, these get strain aged at the temperatures during the baking the paint on the car body stage. Okay, so once this strain aging happens, they gain strength and their performance is enhanced. So, this adds to the strength of the final product after forming is complete. So, the different metals show the different yield strengths and different hardening tendency. In general, increasing the yield strength by cold working, the strength of the metal can be enhanced by cold working, precipitation hardening, grain refinement. So, whenever it is done, so what will be happening in general, increasing the strength by cold working, precipitation hardening or the grain refinement, then you see our the strain hardening exponent value decreases. That is what we can see here. If we go with the higher and higher yield strength, then strain hardening exponent value will be decreasing, okay, with the increase of the yield strength. And a typical just an empirical relationship 70 by yield strength, this can be used to calculate the strain hardening exponent, and this table shows the typical values of the different the metals. Say for the titanium it is very low, and for copper, for brass it is 0.4 to 0.6, for ferritic stainless steel 0.16 to 0.23, 0.4 to 0.55 for austenitic stainless steel. So, different metals show the different hardening exponent. Okay. Now, interstitial free steels means the impurities in form of the carbon and oxygen are very limited. These steels have very low level of the carbon and nitrogen, say around less than the 0.005%. These are produced by degassing in vacuum, and titanium is added to take care of the carbon nitrogen in the solution. Titanium and the niobium reacts in the manufacturing stage of these steels, which preferentially reacts to remove the or eliminate the carbon and nitrogen, and these steels typically show very low yield strength like 150 MPa and the tensile strength 300 MPa, and typical value of the work hardening exponent is 0.28. High strength steels, these are known to be of the high yield strength in the range of 300 to 500 MPa. So, as far as the yield strength is concerned, due to the higher yield strength, they will be offering the greater resistance to the plastic deformation. So, high strength low alloy steels, these are stronger than the carbon steels, and which can vary from 300 to 500 MPa, and this strength is realized through the solid solution strengthening, the grain refinement, precipitation, hardening, these are three main mechanisms. So, the alloying elements are added in such a way they add to the solid solution strengthening and also help in the precipitation hardening, and this is done with the help of elements like vanadium, niobium, titanium. So, which help in refinement as well as the precipitation hardening and the solid solution strengthening. So, high stress obtained in these steels through the effect of solid solution strengthening, grain refinement and precipitation hardening. Okay. So, these steels, HSLA steels offer composed of little higher than carbon content is little higher, manganese is also little higher, and intentionally added phosphorus, silicon and nitrogen in order to gain the effect of the solid solution strengthening. Grain refinement is realized through the rapid cooling from the hot rolling temperature conditions in order to refine the grain size. At the same time, vanadium also helps in refining the grain structure apart from the precipitation hardening. So, increased yield strength actually lowers the formability. So, higher the yield strength, lesser the ductility, lower the formability. Dual phase steels, these steels are combination of the ferrite plus martensite, okay, and these are obtained through the heat treatment process wherein the steel is heated in the intercritical temperature range depending upon the carbon content. Say this is lower critical temperature, this is the upper critical temperature. So, the steel is heated in the intercritical temperature zone. So, we have mixture of ferrite and the austenite, then it will be cooled rapidly to convert the austenite into the martensite. So, we have the colonies or islands of the martensite in the matrix of the ferrite. So, the dual phase steel consists of islands of the martensite and the martensite in the matrix of the ferrite, and it is obtained through the heat treatment in the intercritical by heating in the intercritical temperature zone followed by rapid cooling. These are composed of elements like manganese, vanadium, chromium, nickel to realize sufficient hardenability so that through the rapid cooling martensite austenite can be converted into the martensite. Okay. These offer low yield strength, but high tensile strength. So, there is a very large, the ultimate strength to the yield strength ratio is high. So, 350 is the yield strength and the ultimate strength is 600 MPa. So, there is very wide gap. So, during the forming, deformation largely occurs of the soft ferrite because the metal is composed of both ferrite and martensite. Okay. So, martensite is present in selectively in certain zones in the matrix of the ferrite. So, since the ferrite is soft and ductile, so it tends to deform in order during the metal forming process, so as compared to that of the hard and brittle ferrite. So, during the forming, largely the ferrite face deforms to gain the shape to get the desired shape. In addition to that, in addition to the work hardening, during these steels also get bake hardened. Okay. The trip steel is the another one which is known as transformation induced plasticity steels. In short, it is termed as trip steel. Okay. The trip steels as compared to the dual phase steel and high strength steels offer high strength low alloy steels offer another kind of the benefit. These not just offer the higher yield strength, but these also offer the higher ductility. Okay. So, this is a very unique combination that they have they offer higher yield strength coupled with the higher ductility. So, trip steel composed of the 5% austenite with the remaining or varying amount of the martensite and the bainite. Okay. Since the austenite is soft and ductile, so during the metal forming austenite will be deforming. Okay. And these kind of the steels also experience the deformation assisted transformation. So, in order to avoid that deformation assisted transformation during the metal forming stage, the composition is designed in such a way that during the metal forming austenite does not convert into the martensite under the normal strain conditions of the metal forming, but the austenite converts into the martensite only under the high strain rate conditions which are experienced during the crashes, so that the energy is absorbed during the crash and the passengers are kept safe or the car is also kept safe. Okay. So, the trip steels, so that is why this is mainly used in the automobile, in cars. Okay. So, the trip steel composed of 5% austenite in the matrix of varying amount of the martensite and the bainite. During the transformation, during the deformation, austenite transforms to the martensite, causing the hardness, but what we want that this does not transform during the metal forming stage, but only in the crash stage. So, the so these contain the carbon in such a way that the martensite start transformation temperature is below the room temperature. So, that this austenite is retained even at the room temperature, and amount of the carbon controls the strain level at which austenite will transform into the martensite. So, the carbon content is designed in such a way that austenite does not transform into the martensite unless there is a crash kind of situation. The strain level is high enough so that no additional martensite is formed during the metal forming, but it is formed during the crashes only, so that the energy is it can absorb energy without adversely impacting the people inside. Martensitic stainless steel is another one which offers very high yield strength and very low ductility, like say 1400 MPa yield strength and 5% of the ductility. So, this is very unfavorable from the formability point of view. So, in these steels, austenite transforms to the martensite through the rapid cooling just after the hot rolling, and these steels must have enough alloying elements like manganese, silicon, chromium, molybdenum, boron, vanadium, nickel, in order to ensure the high hardenability and the lower critical cooling rate, so that the austenite can easily be transformed into the martensite to realize the high strength of these steels. High tensile strength of these steels can be estimated through the simple relationship of 900 MPa plus 2800 multiplied by the percentage of the carbon. Okay. So, carbon content directly determines the kind of the strength that will be there. In any case, the minimum tensile strength is 900 MPa. Further higher level of the strength addition will depend upon the carbon content, okay, which is present in the steel. So, amount of carbon controls the strength level, and because of the high yield strength and low ductility, these steels offer very low formability. So, now I will summarize this presentation. In this presentation, basically I have talked about the factors which are controlling the ease of metal forming, and there are different types of the steels with the varying microstructural features, different phases, and which in turn determines their yield strength and the ductility and work hardening tendency, and that in turn affects the ease of metal forming. Thank you for your attention.